Hello, I'm Yamila Miguel. I'm assistant professor at Leiden Observatory and the Netherlands Institute for Space Research. And today I will tell you what do we know and what we don't know about the atmospheres of the giant planets in the solar system. Let me start telling you why we care about studying these planets. And the reason why we want to study giant planets is because at the beginning of the solar system, the star was born, the sun was born, and from the remnant material of the solar formation, all the rest of the planets of the solar system were born. And the first planets that are born from this disk that develops around the star are the giant planets. They form only in a few millions of years, which is a very tiny amount of time in astronomical units. And they do have in their interiors and atmospheres very valuable information to understand the origins of our solar system. Also, the reason for that is because giant planets remain very close to how they were at the beginning of their formation. It's not that they have internal processes happening, like, for example, in rocky planets that have plate tectonics, that have a lot of internal evolution. Giant planets, because they are mostly made of fluid material, then they don't change the same way as rocky planets do. And that's why they remain so primordial in a sense. And that's why we want to understand more about their interiors and their atmospheres. Now, how is that we study the giant planets in the solar system? Well, of course, they are close by, again, talking in astronomical units. And therefore, this means that we can go there. So there were many missions that went to the giants. I named all of them here. So you see that the planet that received most of the missions is Jupiter. And the reason for that is because Jupiter is the closest giant to the Earth. The others are farther and farther away, and therefore is harder to reach. So for Jupiter, we have the pioneers that went there, the Voyagers, the Cassini mission, the Galileo mission, the New Horizons, and Juno. Some of them did only one flyby, right? For example, the Cassini and New Horizons, they needed to go close to Jupiter to actually get the gravitational kick, the gravitational acceleration to reach the outer solar system. But nevertheless, when they went around Jupiter, they sent us information. For Saturn, we have Pioneer 11, the Voyagers 1 and 2, and the Cassini mission that was an amazing mission that gave us huge information, not only on the planet, but the rings and the satellites as well. For Uranus and Neptune, you see, we have only one passage of the Voyager 2. So these two are really very unknown for us. We don't have a lot of information coming from space missions. But of course, that is not the only way that we get information from these planets, because as you know, some of them, like Jupiter and Saturn, they are like, we can see them with our naked eye. We can really see them with a small telescope, even binoculars. So we can also get information from the ground, from the Earth, and also from telescopes that are orbiting around the Earth. And one example of this is the JWST, that is a telescope that has been working since a year ago. It took a long time really to develop. It's a pure technological marvel. And here what you can see is how the telescope assembled itself on space. It's a really huge, huge telescope. And it involves NASA, but also the European Space Agency that was responsible for one of the instruments and also the launching. So it's really a team effort of astronomers around the world to have that telescope out there. And the telescope is the biggest we've ever put on space. And here, for example, as a comparison, I'm showing you the mirror of the JWST compared to the Hubble Space Telescope. That was the one that we had before. They gave us all those amazing images of galaxies, for example, and the cosmic background. Now you see that the JWST is way bigger. And of course, in astronomy, this is better because we need, the bigger the telescope, the better it is to collect all the photons, all the light that is coming from the stars and the planets and everything out there. So we are using now JWST, we are using, in the past, we also used the Hubble Space Telescope, and we are also using big telescopes from the ground, including, for example, the ALMA array that is in Chile, and those are radio antennas. Sorry, not radio. ALMA people would hate me if they hear me saying that, but they are long wavelengths than these ones that are visible. So then we use all those technologies to try to understand better the planets and the stars and the galaxies. And that, of course, includes also the planets in our solar system. Although sometimes they are a little bit too bright for some of these technologies that are developed more thinking of very dim objects far away. So then when you put them into all these light, you know, they are giving a lot of light. That's why we see them with the naked eye. So sometimes we need to develop special techniques to use these great telescopes for these objects. Now, let me show you a few of the amazing pictures that we have that we got, especially from space. So this one is from the Voyager 2, and this is Neptune. So I started from the farthest one to the closest one. And you can see here, for example, that blue, darker blue thing that you see is a big storm that is happening in Neptune, similar to the great red spot in Jupiter. That's something like that Neptune has. We have here Uranus, as seen from the Voyager 2 as well. That also looks more greenish than Neptune, I could say. We used to call them twin planets, but they are not really twin. They have many differences between them. The only similarity that they have is their mass and radius that are close by, but that's definitely it. We have Saturn, as seen from the Cassini mission, and here you see, for example, this is one of my favorite images. You see the shadow that the planet puts on the rings. Even if you look at the pole, you see a perfect hexagon in the pole that is a result of the dynamics in the atmosphere of Saturn. And here I put a few, not only one, but a few images taken by the Juno mission. So the Juno mission is a NASA mission that has been orbiting around Jupiter since 2016. I'm part of the science team of the mission, and very proudly so, because it gave really amazing information on Jupiter. It changed the way that we were looking at the planet. Not only the atmosphere, the magnetic field, but also the interior. I particularly was studying the interior of Jupiter for this mission. So here you can see a time lapse that was made with one of the orbits of Juno around Jupiter. And you see that it was passing very, very close to the planet. So the closest passages were at 4,000 kilometers above the clouds, which is really, really, really close. And that's why we have these stunning images of the planet that were created because of that. We can see that we can even tell the details of the clouds and see all this turbulence. And of course, all of this is giving us information to learn a little bit more about the weather in these planets. Now, we don't only have images from space, we also have images from the ground. And here are images taken by this space telescope, the JWST, so the 4 giants in the solar system. And you can see the rings in all of them, because the 4 giants have rings around them, not only Saturn, but of course Saturn's rings are the famous ones because they are bigger and they are brighter, but all of them actually have rings. So you can see here the rings of Jupiter that are very, very thin. The rings of Saturn, of course, that are bright and beautiful. Uranus has also very impressive rings, and you see them tilted because the planet is tilted. So Uranus doesn't rotate like this, but it's like tilted and it rotates like this. We think that that's due to a collision that it suffered during its evolution long time ago. And here you see Neptune as well, with also its rings. So this is also a great imaging from JWST. Now, what do we know about these planets? What are the things that we know? Well, of course, we know the sizes that they have. And here you can see a comparison of the sizes of the 4 giants. Well, actually the entire solar system, right? We have the giants, we have the sun, we have here on the corner, left corner, the rocky planets. And you even see some of the dwarf planets beyond Neptune. And of course, these ones are the biggest by far planets in the solar system. All of them together put more than 90% of the mass of the planets. And but still, if you compare them with the sun, they are tiny, right? So this also puts in perspective how small the Earth is compared to the rest of the things out there. What can we say about the composition of these planets? Well, we have, if we compare, for example, the composition of Jupiter with that of the Earth, you see that the Earth is mostly made by what in astronomy we would say heavier metals. But if a chemist hear me, they will probably be horrified by this. But most of the things in the universe are made by hydrogen and helium. So in astronomy, really is like mostly hydrogen and helium and everything else. But if you compare it with Jupiter, for example, Jupiter is a good example. It's mostly made by hydrogen and helium. And then it has a tiny percentage of all the other elements in the periodic table. So these 2 planets are very different from each other, right? The Earth and Jupiter are different things. And that's why they even have different categories. Ones are rocky planets, the other ones are gaseous planets. And gaseous because they are really made of a fluid material. I'm not daring to say gas because at the height, when we go deeper into the planet, the pressures are so high that then all that gaseous material became really more like a fluid. But they are definitely, there is probably nothing solid inside these planets, not even the cores, although we are not completely sure of what happens in the core because it's very difficult to replicate those conditions in the lab. Well, I would say almost impossible to replicate those conditions in the lab. And therefore, it's difficult also to study the phase that this material in the core of the planets would be. So we don't know if the cores are made of solid material or most likely, I would say, fluid material as well, of mixed rocks and material that forms rocks, material that forms ices, and hydrogen and helium as well. Now, if we compare Jupiter with the solar composition, we see that the giant planets are actually closer to a star than really the rocky planets are. And for some time, people even call them failed stars, but they are not. Probably they form in a different way. At least that's what we believe from these giant planets in our solar system. So I mentioned that the planets have no solid material. So take out of your mind the idea of a solid surface that we could walk on. That doesn't happen in any of the giants in the solar system. And it's interesting also to see the compositions, which things have we learned about the compositions of the atmospheres in these planets. So here is the composition of Jupiter's atmosphere. Remember, we can only measure what's happening in the atmospheres of these planets. Is the only thing that we can see. We cannot really go into the interior and make measurements. So all of these are the elements that have been measured in the atmosphere of Jupiter, and I put them here in red on the periodic table. So then you see actually that there is a tiny amount of those that we have measured. Probably many of the others are also in the interior, but the amounts are very small. So it's also very difficult to measure. So we can only measure the ones that have a substantial amount in their atmospheres. Now, if we compare what we know with Jupiter with Saturn, and Saturn is the blue now in the periodic table, you see that we know a little bit less about Saturn than what we know about Jupiter. And the reason for that is because for Jupiter, we had the Galileo probe that entered into the atmosphere of Jupiter and made in situ measurements. And this was in the 90s. And that's why we have such a great information of Jupiter's atmosphere and not so much on Saturn, because we didn't have a probe into Saturn's atmosphere. If we go to Uranus and Neptune, you see that we know them less and less. And again, this is because from the space, we only had one passage of one space mission going there. and they are also farther away, and therefore they are dimmer, so they are also more difficult to observe from the ground. Although we are definitely trying to get better information on these planets. Now, let's move on a little bit on information that we learned with the Juno mission on Jupiter, because this is all very recent and it's very exciting. So the Juno mission has on board of the spacecraft a microwave radiometer. And for that, that allowed the spacecraft to actually see passing through the clouds of Jupiter that are very thick, very opaque. But we could go inside and try to understand a little bit more about the structure of the atmosphere, and not only, you know, the upper layers. And if we look at the Great Red Storm, this is like a huge hurricane that is around Jupiter and has been there for centuries. We've been observing this since the Galileo times. And we know that it evolves. If we look at it in time, we see that it varies the size. So sometimes it swallows some of the other tiny vortices. There is all these that we see in a static picture is really dynamic. And with this spacecraft, we actually could see how deep is the Great Red Spot. And it was the first time that we could actually see that. We know that the Earth comfortably enters in this, but what about the other direction? What about the depth of it? And we could map this storm at on these different channels on the Juno spacecraft, and we actually learned that the Great Red Spot probably goes up to something like 500 kilometers maximum into the interior of the planet, which is really, really, really tiny compared to the huge radius of Jupiter. So it's very shallow in a sense in this spot, which is also helping us to understand more about the dynamics of the atmosphere of Jupiter. Now, what about the rest of the bands? If we look at Jupiter, and now I'm showing you a movie taken by the Cassini spacecraft, you see that it has these bands that move in different directions, in different velocities. You have to understand that the giant planets rotate very quickly, very quickly. Jupiter, that is, you saw how big it is compared to the Earth, rotates in less than 10 hours. And all that rotation, very fast rotation, is really what drives the weather in these planets, the climate in these planets. And these bands that you see are really created by this Coriolis force that is created with this huge rotation. And that's why we have these dynamics happening in these planets. Now, of course, one question is, we know that the interior of the planet, let's say the bulk of the planet, rotates at a certain speed. But when we observe these bands, we see that they rotate at different speeds and different directions. So how deep these winds extend into the planet? This was a question that we had for a very long time and that we could also solve with the Juno spacecraft. In this case, mostly using information from the gravity field. And what we did was to understand that these bands that we observe extend up to approximately 4% of the radius of the planet, which is 3,000 kilometers more or less. And then when we go deeper into the planet, we have that the entire fluid that we have there rotates as a rigid body in a sense. So this was one of the studies that we did, and I was proudly part of to understand some of the dynamics happening in the atmosphere of this planet. Now, what about the other giants? We also could make a similar analysis in Saturn's atmosphere using data from the Cassini spacecraft, and we determined that these bands that we observe in Saturn extend up to approximately 8,000 kilometers. 9,000 is the last number that we have for them. So they actually extend deeper into Saturn than they do in Jupiter. And Uranus and Neptune are highly unknown. And of course, this is, again, because we have very little information. So there are some speculations with the little gravity data that we have, but we cannot really tell much about those planets. So just wrapping up, what do we know about these planets? We know that their main composition is closer to the sun than the Earth. We know that some of the most abundant elements in the solar system were observed there. We know that the interior is mostly made by fluid material. We know that the weather is driven by this fast rotation that they have. The winds that we observe do not move at the same speed as the bulk of the planet, and that is, of course, true for rocky planets as well, right? Our atmosphere doesn't move at the same speed as we do on the surface, and we know how deep these winds extend into the planet. Now, let me use a few more minutes to understand what we don't know about them. And there are lots of questions on the giant planets that I'm not going to enter, but really the solar system is not known. Everything is not known at all, even though it's very close by, right? But still, there are many things that we don't know. For example, I show you those bands and they have different colors, but we don't know why they have those colors. We don't know exactly which particles, which composition is causing the colors that we see. Especially in Jupiter, the pole of Jupiter was recently discovered to be blue. And we think that that is a scattering of particles very high up in the atmosphere, but there are still many questions that we don't know about that. We don't know which are the masses of metal. So how many elements, how many heavier metals they have in their interior. We know that they are mostly made by hydrogen and helium, but the rest of the elements is still something that we don't fully understand. We don't know how massive are their cores. And this is a very big question because it's really helping us to understand how the planets form and evolve. And this is something that we still don't know. We don't know how are their interior structures. We have, of course, some ideas, some very advanced ideas of things that we learned recently, but still there are many open questions as well. Interiors is definitely for another talk. We don't know how they form or where did they form. We know that the giant planets moved around, migrated during their formation. They are not these days in the day where they were born. But we don't know exactly where they were born. Were they born closer to the stars, to the sun, or farther away, or where do we see them today, right? So these are still questions that are very crucial questions to understand the formation and evolution of the solar system, and to also understand our own space in the solar system as well. We don't know why the poles of Saturn and Jupiter are different. We have some ideas about the dynamics there. You saw that perfect hexagon on the pole of Saturn, but we don't see that in Jupiter's pole. And about the storms, how they evolve, we are starting to understand now all the turbulence and all the dynamics and the movement of all those storms, that is very, very complex. And finally, we also don't know about the rings. This is not really about the atmosphere, but it's one of the questions. We don't know if they are new, if they are old, if this is something that they only have for a few thousand years and we are lucky enough to observe. So there are really lots of questions about these planets, and I'm just here in mentioning a few that I thought were relevant for this talk. Anyway, I hope that you have lots of questions. Usually, I think a talk is successful when people have more questions. So I hope that to interact more with you, and thanks for your attention.